Hello, everyone, and welcome to this iteration of the Women in Combinatorics virtual colloquium. Thank you all so much for attending today. I am thrilled to introduce our speaker, but first, some housekeeping. Just a reminder, feel free to keep your video on or off, whatever you prefer, and ask questions to our speaker whenever you can. I'll be monitoring the chat if there's anything that comes up or any technical problems that anyone has. Our talk is recorded today, and I'd like to let you know of our new YouTube channel where we will be posting all of as many talks as we can, So if you have friends who couldn't make it today, please feel free to send them, I guess, this link for those of you who are already watching on YouTube. So thank you again very much. So without further ado, I'm pleased to introduce our speaker for today. Anna Stoica from Columbia University is going to be talking about some very interesting graph theory today. So whenever you're ready, please take it away, Anna.
Thank you so much, Erin, and thank you everyone for being here. It's really exciting to talk to you about my work on graph theory and different methods we looked upon to understand inequality. I'd love to hear your thoughts all throughout the talk. If you have questions, comments, anything, please feel free to interrupt at any point. And with that, I'm going to start, this one, sharing the slides. Great. So a lot of my work focuses on thinking about diversity and inequality on social networks and thinks about what is the role of social networks in creating inequality between different groups, particularly when you have different algorithms that are giving resources to people or information and so on. So two of the applications that I've been looking at that I'd love to talk to you today about are related to the social influence maximization problem and to recommendation algorithms. And in both of these, in a sense, what people get out of these algorithms is either information or new connections. So when we think about inequality in networks, we have to think about like different groups that are connected differently with each other, and this can represent different demographics, political affiliations, interest group, and so on. And we think about how do we evaluate a biased outcome when you deploy an algorithm on them. And the very question of what does it mean for an outcome to be biased relates to the specific application that we have in mind. So for example, in the case of diffusing information, in the social influence maximization case, we would think about, is there a pattern of certain people or groups that are don't get to be in this information loop? In the case of recommendation algorithms, we think again about the pattern of groups or people who are getting fewer connections or not recommended as much as everyone else. So through this lens, I wanted to talk, I'll start with talking about the social influence maximization problem, which most relates to how information gets propagated through a network, through basically through relational data. And that relates to the news that we read, technologies you hear about, how you run different marketing promotions, and how you would disperse general information to people like in a public health issue. And these last two in particular require very different kind of campaigns or algorithms. In the case of running a marketing promotion, you may want to think about targeting like a very specific group of people and running a targeted campaign to make sure that the information you give is relevant for that particular group. Whereas in a public health issue, we would run like a large campaign based on the assumption that everyone in our population is interested in the information that we have to give. And this is the setting that we were focusing on. So we're not thinking about how to target specific groups, but how to efficiently disperse information to a population in general. There's a lot of work that has been thinking about this in the context of course, how do we distribute information about like healthcare issues or vaccine information related to COVID-19. There's other related to thinking about different kinds of opportunities. This is a study being done that was done on how do you diffuse information in local communities about, for example, microfinancing loans and what structures in the networks are important to diffuse information efficiently. Similarly, this is a study that thinks about how do you raise awareness about HIV among the homeless youth and how do we leverage the local connections in order to do that in an efficient way. So there's this notion that comes up that, access to information is actually access to opportunity and healthcare, and it's important to think about the groups that are represented in this information loop. Now, I wanted to get to think about how do we define this problem, what kind of algorithms we think about. So to start formalizing this kind of a problem of social influence, oftentimes we think about a network, G in this case, with people connected to each other, and we think about a particular diffusion model. In this case, we're looking at the independent cascade, which simply means that if someone hears a piece of information, they give it to their friends with a certain probability P, who then give it to their friends with a certain probability P, and this process cascades, and it's done in an independent way from one another. And the purpose here is to get this information to as many people as possible in the end. So of course, if you as a central designer can give this information to everyone in your population, that's great. You're done. But that's not often the case because you have constraints that are either physical, computational, your network is large. So what you have to do instead is pick strategically a few people that are among your budget, call the early adopters or the seed set, and rely on them to diffuse information. So the way you would choose these people, of course, turns into this optimization problem. And if you choose people that are more central by some metric of centrality, you're going to do better at diffusing information. If you choose people who are less central, you might do worse. But we can think about formalizing this as a particular optimization problem in which we have our initial set. We're trying to find out the best one depending on our constraint, on our diffusion, and on a diffusion function phi. And this problem turns out to be pretty hard. It's NP hard in general, but there are several approximation algorithms that try to solve it for different using different metrics. For example, thinking about centrality metrics, degree is generally doing pretty well, distance centrality, eigenvector centrality, and so on. Other methods that work iteratively, like greedy, and greedy does really, really well. But it's computationally expensive and it requires the full network information in order to create a good campaign. Now, what happens when you have different kinds of groups in your network? And here I'm again portraying in blue and red, which can represent, again, demographics. They can represent political affiliations, affinity groups, or any kind of like community level data. And here, there's a recent work showing that, well, if there's bias in centrality measures, then that will actually get reproduced in the outreach as well. So if there's a group that's like less central and more peripheral to the network, they're going to be less represented in the early adopters and overall in the outreach as well, which means that you end up with groups that are left out of this information campaign. And as I mentioned before, that becomes an issue when you think about information that pertains to everyone, particularly to like, healthcare related information, opportunities, and so on. And that's the problem we're trying to fix. So in doing that, there's a bunch of solutions. Some of them relate to imposing a statistical parity constraint in this optimization function that's based on greedy algorithms and simply saying, well, I just want the outreach to look like how my general population looks like. If I have 30% people of the red label, I'd love to see that in the outreach as well. Among people who hear this information, I'd love to see 30% of them of the red label. So, and what happens with this kind of solution is that you end up with this fairness efficiency trade-off, which means the following. It means that if you don't constrain the problem and you simply try to solve it based on some centrality metrics, for example, you end up with a pretty good outreach. A lot of people hear this information, but one of the group is underrepresented. With such parity constraints, you might get better representation of who heard this information, but there's just going to be fewer people. So this is what this trade-off means. Now, in this work, we take this different approach and we work with different kinds of centrality measures in order to understand how we can leverage connections and network models in order to try to do both and to make sure that we are diverse while giving this information to as many people as possible. And what we find out is that, well, we can use a model of network growth that tells us when exactly you can actually get more equity and a more efficiency at the same time. So you can be more diverse and more efficient in the outreach at the same time for a particular set of conditions that work pretty well in practice with our data too. And I wanna spend some time just talking about the model and how we, what are we leveraging in terms of like graph theory to get to this kind of results. Are there any questions so far? All right. Great. So this project was from last year, almost 2 years ago by now, with my advisor, Augustine Chantreau, and our collaborator, Jesse Shinihan. And the vision is that the bias that you see is actually a sign of inefficiency. And thinking about tapping into inactive communities in the early adopter set will actually do well in increasing your diversity. So we want to compare that with, if you work with some traditional heuristic, you would seed and you would choose this set of the seed set in an agnostic way. You would ignore the labels and you would assume that takes into account the network structure to begin with, like we said before. What we do is to say, well, we can be aware of the labels and aware of this community affiliation, and we want to make sure that actually in the early adopter set, we have better representation of these different communities. So that might mean that we're choosing even less connected people to begin with, but we'll see how that plays out. So what we're doing is we're proposing these two heuristics. Sorry, I'll get to that. So we're proposing these heuristics that try to get statistical parity in the campaign, which turns into a different optimization problem. But this is actually much easier to think about and to approximate given the heuristics and the network model of growth with different communities that we have. So I want to show you how these heuristics would look like. To begin with, if you have an agnostic seating, like I mentioned before, and if you're choosing, for example, a degree heuristics, what you would do is you would order people by their degree, and you would choose the top number of them, top K or something, depending on what your budget constraints are. And in this particular setting, the blue nodes have higher degrees, so you're going to get some underrepresentation of the red nodes. Let's say if they're in equal amounts, then you're going to end up with more blue nodes, which is something we're trying to fix. So what we're proposing is two heuristics that are based on trying to diversify the set of early adopters. One of them, called parity seeding, we can enforce the statistical parity strictly. We can say if there are equal numbers of red and blue in general, we want exactly equal number in the early adopter set. So what we're going to do is, well, we have to choose more of the lower degree red nodes and fewer of the higher degree blue nodes in order to achieve that ratio, because we have to keep the same budget. We also propose something in the middle, diversity seeding, which is a relaxed version of parity seeding, in which we're saying we'll allow some wiggle room in that statistical parity condition. So it's somewhere in the middle of agnostic seeding and parity seeding. And again, we have to keep the same budget of that. And we want to see how these perform. So the model for networks that would tell us the intuition for how these heuristics perform is the following. We're working with this bias preferential attachment model in which we have two communities. Let's say you have a majority in blue and minority in red, and a rich get richer effect. So you at each point in time, a new node comes into in the network, and it connects with probability proportional to the existing node's degree. And that's the preferential attachment part. The third part is homophily. So if people have different labels, actually connection is accepted only with a certain probability, which creates this clustering effect of blue nodes connect more with blue, red nodes connect more with red. So this part of homophily, we notice in a lot of online networks, and there's a lot of networks related work that talks about this phenomenon of like similar people connect more with each other. And that's something we notice in a lot of the data sets we used to. The rich get richer effect is something that we see in a lot of online networks as well, where you see a very skewed degree distribution with few people having very high degree and a lot of people having very low degree. And this model is particularly interesting to look at. It's been proposed recently, and it's been shown to exhibit inequality in the degree distribution of the two communities. So this kind of model, preferential attachment, generally follows a power law degree distribution, which is what we notice in a lot of these online settings. And more than that, what happens when you have two communities is that you get two power law distributions, and they have different coefficients. The fact that they have different coefficients is what creates inequality in the centrality metrics, because we're not looking just on average that the degree is different between the red and the blue. But for nodes of very high degree, for example, that's where you're going to see that you're going to see way more blue nodes than red nodes. And as the degree increases, because it's a power law, the fraction of the red nodes will just vanish. And this is a problem that people have studied recently, this problem of social influence, have noticed that, well, in the centrality metrics, people are not well represented among different groups. And this is one phenomenon that will explain like how different representation will occur. What's interesting about this model is, again, it's the fact that the relational data here is very, very important, because if you have these two communities, they're separate. So if you just have a minority and majority that connect among each other, but not across each other, you don't get this difference in power law distribution. They do follow power law, each of them, but it's the same coefficient. There's no inequality there. It's when they start to connect with each other that you get to see more inequality. It's when, you know, red nodes in the minority group start competing for connections with the blue nodes, is where you start seeing this kind of difference. So this is where we see that, you know, a metric like degree will be biased towards the minority, towards the majority, for example. Now, I want to show you quickly what's happening with our heuristic using this model, and I'm going to show you an illustration of that. The first thing that we get is that, well, both diversity seeding and parity seeding would lead to a fair outreach for the same budget. And this claim is relatively intuitive, because we're trying to add more of the minority group in the early adopter set. And because minority connects more with minority, because we have homophily, that trickles down into the outreach as well. And it's a part of the model. The second part that's less intuitive is that both of them, diversity and parity seeding, can actually outperform agnostic seeding in the outreach. So even if we have this constraint of we're going to add minority nodes that have lower degree, they can actually get better results particularly when our campaign is large enough. And we can compute exactly what's the size of the campaign that will get us that amount. And I'm going to show you how that looks like. But the main idea is that, well, if you have a small campaign and your budget is really small, agnostic seeding is going to perform the best in getting you as many people as possible. You will have a small trade-off, which is really small in practice, between being fair and being efficient. And when you have a really large campaign, you can be strictly fair and efficient at the same time. And when you have a medium budget, which is often the case, that we don't have a very large campaign budget for running these, that's when having a relaxed version of fairness gets you to be more fair and more efficient. So I want to show you how this looks like. Given our heuristics. So this is a theoretical analysis in which we're looking at simulating different networks based on the model that I mentioned before. On the x-axis is the minority fraction. And this is a network of about 53,000 nodes that more or less is trying to look like the real data that we have as well. It has two communities, some homophily factor, parameter, and so on. So on the x-axis, we have this minority fraction. For example, 0.10 simply means you have 10% minority in red and 90% majority in blue. And as we move towards the right side, we're getting to more and more equal communities, in which 0.45 means that you have 45% a minority in red and 55% a majority in blue. Each of these points is a network simulated more or less from this kind of parameters. And on the y-axis is the seed set size. So what we're plotting here in different colors is who does better in terms of the outreach of these different heuristics. So I'm not showing the numbers of the outreach, but I'm going to show you that for the data to have something in mind of how that would look like. What we get here is, though, the following. So each of this region is when one of the heuristics performs better than agnostic. You will notice that diversity always performs better than parity, but that's because it's a relaxed version of it, so it's always going to do better in the outreach. Now, In the orange region, that's where agnostic seating performs the best. That's the region in which you're going to have a trade-off between being fair and being efficient. We notice that as the seat set size increases, we are transitioning into this blue region, which is where diversity seating actually will perform better than agnostic. And the phase transition boundary here is decreasing, it's monotonic, which shows that, well, when you have more equal communities, it's easier to be more fair and more efficient at the same time. When you choose from the minority group nodes to be more diverse in the early adopter set, they have pretty high degree because they're pretty well represented. So you're not losing much. It's easier. You need fewer and fewer seat sets in order to achieve both of these objectives. Now, as we continue to increase the seat set size, we see that at some point we transition into this purple region. And in this purple region is when being strictly fair, parity seating, also outperforms agnostic seating. And we see that we need a lot more seat sets to begin with in order to achieve that. But the interesting part that we notice also is that the phase transition here, the boundary of that is no longer monotonic. So as the communities become more equal, at some point it becomes harder to be strictly fair and efficient at the same time. And an intuition for that is that, well, when we're choosing more of the minority group, when the network is more equal, this group already heard this information. There's some nodes of relatively high degree there. They're not completely out of the loop. So it's harder to be strictly fair given that they're still in the minority. Whereas when we have a very unequal network, choosing some nodes from the minority group actually gets you to a whole new community that we haven't reached yet. Whereas just choosing from the majority group kind of lets you be stuck into that majority group because you would have overlapping sphere of influence of blue nodes connecting with other high degree blue nodes. Are there any questions so far, by the way? I'm gonna stop here to check. All right, if not, I'm gonna keep going for that. So I wanna show you, just a quick illustration of how the data looks like for this kind of work. We use this DPLP citation data sets that contained basically 53,000 nodes, and the two communities that were men and women. And the women were about 18%. So we're about at this like particular vertical line in our simulations. So let me show you what happens for if your seed set starts at, say, 1,000 nodes. For a probability of diffusion, you end up with these results. So total outreach, this is average over many simulations. We get that agnostic seating performs the best, confirming that we are in this trade-off region that's orange. It is parity seating and diversity seating are both more fair in terms of how many women they get in the outreach. But that's how they were designed to be. Now, when we increase the seed set size to say 5,000, we are expected to be still in this orange region, but the data actually ends up being more, let's say the theory is more conservative than what the data looks like. So what we get is that diversity seating actually starts to perform better. And it's not by much, but given the fact that we removed some high degree nodes and added some lower degree nodes, and they managed to not only compensate for that, but also overcome that, is exciting to see. And so what we see is that we actually got to this blue region already. And that's what I mean that the theory is a little bit more conservative than the data. So as we increase the seed set size, let's say we're about like 9,000 seeds, we're actually now transitioning in the data in the purple region, where parity seating is also starting to perform better than agnostic seating. And understanding this particular model was very important for us to understand, well, if you have these different communities and you understand where does inequality come from in their connection, you can target them in a way that can make you be more efficient and fair at the same time. And the fact that one community is not part of this information loop means that we're actually biased and inefficient to begin with. And this is the end of this project. I want to show you how This kind of models can be really helpful for other purposes, and I'm gonna talk about our recommendation project as well. But if there are any questions here, do let me know. All right, so this project was with my advisor Augustine Chantreau and our collaborator Christopher Reeder. And in this project, we looked at different kind of data sets. We looked at the PPLT data set. We also looked at this other data set, Instagram, that we used in both projects, but I'm only mentioning here. And this data was interesting. It had about 500,000 nodes, and it had a little bit more women, but men had higher degrees. And that didn't mean anything about Instagram itself, but it just meant that, you know, it's something about the data, how the data was collected, and so on. But there's some inequality in the degree distribution. And we were trying to understand what happens when you have recommendations on this data. Now, this data was collected in about 2013, which is when Instagram didn't have yet this who to follow feature into it. So the data that you see is actually devoid of recommendation of a recommendation algorithm. It only contains these organic connections. And we wanted to see what happens when you have different recommendations. So we simulated a bunch of them to see how does the degree distribution change in that case. So when we did that, we actually noticed that the imbalance between the two groups about men and women actually got worse. A quick illustration of that is that in the original data, if we looked at people who had degree at least 10, so this is an interaction graph of liking or comments, that's what the edges are. So if you had at least 10 likes or comments from other people in general, that's where you got to see that you got 52% men and 48% women. And the women were a bit in majority to begin with, so that's where you get to see a little imbalance. We tried different recommendation algorithms. Here's the illustration for a random walk of length 2, where everyone gets a recommendation. And when we again count people who have degree at least 10, there were 64% men and 36% women. And again, this doesn't mean anything about the men and women in this case. It's just two groups in which we see that inequality in the degree distribution got worse. So I want to show you what happens actually in detail with different recommendation algorithms. So we tried different ones that are based on friends of friends, like Adamic Adar, this random walk of length 2. We tried others like common neighbors, but for these two, this is a plot of, on the x-axis, the degree distribution, so the degree. And on the y-axis is the percentage of women among those with degree at least on the x-axis. So blue is the original graph, and the circles around it just means the proportion of the population at that particular point. We start with everyone being a degree at least 1, because there is about 54% women, which is where the dashed line is. So everyone has degree at least 1, and there's 54% women among those. As we move towards people with higher degree, we see that at some point, the percentage of women among them drops to 0. And what we see when we apply an algorithm like Adamic Adar or a random walk of length 2 in green and red is that the percentage of women among those with degree at least X drops to 0 much quicker. So that's what we mean that there's an amplification of inequality in the degree distribution. It's not only that on average, women had lower degree, is that when you start looking at people with higher and higher degree, that's where you get to see a vanishing fraction of one of the groups. And that vanishing fraction happens much quicker for when you have also recommendation. So we used again some models of network growth very related to what I mentioned before in order to understand this process. And you know, in the previous project, we mentioned this model of organic growth in which we work with simulating how information would be diffused. And we noticed that, well, of course, in that model, we have preferential attachment, and homophily leads to this skew degree distribution. And this is the organic growth model that we're comparing with here as well. Now we added to this model a recommendation in which every existing node connected with someone through a random walk of length 2. And what happens here is the following. We know that in the original one, we got these two power law distributions with two different coefficients. With recommendation, we're also able to show that you still get a power law distribution for each of these two communities for red and blue. But more than that, the two coefficients actually are growing further apart. So the gap between them is increasing. And this is what you see illustrated in previously, where you see that the proportion of the minority drops to 0 much faster. And this is how it would look like as an illustration of this particular process. The data that we looked at, we of course looked at the degree distribution, and it does follow this trend of like women connect more with women, men more with men, and it was really skewed as well, like this power law would tell us that it would be. So what's interesting about this is that we saw that, well, there's 3 conditions. The fact that you have 2 groups, homophily and the preferential attachment, are actually necessary and sufficient to show this kind of results. Without any of them, you don't get this. Without homophily, you get the same, you get preferential attachment, you get the power law, but they have the same coefficients. You don't get this inequality that we see in the data. Without the 2 groups, of course, you don't get any of this. You just get a preferential attachment model. And without the preferential attachment, you might have different kind of connections, or you might have an exponential degree distribution or others, but preferential attachment in particular simulates this power law distribution that we see a lot in a lot of these networks. So that's, I wanted to show you a short, I think we have time to show you a sketch of the proof of how do we actually get to such a result, and how do we find the degree distribution for this kind of models. And I hope that's, I was thinking that would be of interest to the group, and I'm happy to discuss it more. What we begin with here is that, well, if we start looking at the wealth of the red nodes, meaning the fraction of edges that are directed towards them. So this is the red and the blue nodes, let's say, and red are in some fraction R. If we look at the fraction of edges towards them, what we see is that the rate of growth of this fraction actually would converge as the network grows to infinity. And it grows towards a fixed point. And what you would expect is that it should be around, in a network without inequality between the 2 groups, it should be more or less the fraction of red nodes that you get in general. But in our networks, you get to see that it's actually less than the fraction of red nodes. So that's where that's the imbalance that you start with. Now, when you add this recommendation, actually the fraction of edges towards the red community decreases. And it decreases in this asymptotic analysis as well. What do we do with that is that, well, we're looking at an evolution equation of when do nodes of different degrees get new links. So they can get links either randomly or through preferential attachment, right? And then we can define the rate at which nodes, for example, red nodes receive edges through randomness, and the rate at which red nodes receive edges through preferential attachment. And this being just like the nodes of degree at least k would receive those edges. What we get to see is that, well, the proof for finding that this is a power law and finding the particular coefficient shows that the coefficient is actually depending only on preferential attachment, which makes sense. If you have edges only through randomness, you get something like an Erdős-Rényi graph in which you don't get this power law distribution. And in computing them, we were trying to compute them to find and to prove this kind of result. And we tried to use the evolution equation to find a closed form solution for these coefficients. But in doing so, it actually turns out to be really, really messy. So there's a different technique we used here to think about, which is that, well, at equilibrium, the rate at which edges towards the red community will appear will equal the current fraction of red edges, because it's a system at equilibrium and it will not evolve anymore. So that gives us actually an invariant equation that models the asymptotic dynamics of this degree distribution. And how does that look like? Well, we can write it down. And for, I have these inverted, but for a recommendation model and for an organic model, you basically get to see that the fraction of red edges, depending on that are created through preferential attachment and through randomness, should equal to the fraction of red edges at equilibrium. And what you get to see is that, well, if the fraction of red edges towards the red community is different in recommendation versus organic model, you get to see that, to prove basically how these coefficients are also starting to differ. And that's where we get to see that the power law coefficients are growing further apart. And the proof for finding that this is actually a power law is similar to just the general proof for a preferential attachment, with a power law computing the probability of new edges being created for different communities and approximating it with a power law coefficient. So this is the, that's what I wanted to end on here, but I wanted to mention another thing, which is, homophily actually plays a very interesting role. We saw that when you have like a majority group that has a degree advantage and homophily, you get to see that that's where the degree distribution favors the majority, and you get to see bias in centrality metrics and so on. It affects recommendation as well. But what we saw in the Instagram data was that the women were slightly in majority, but had lower degree. And that can happen. That can happen particularly when majority has actually doesn't have a degree advantage, and minority is more homophilic. And that's where a degree, this like equation or this inequality between the degree distribution coefficients actually can be inverted. And that's where we get to see actually that recommendation will make things worse. So it's not that recommendation created inequality that always favors a majority group, is that it amplified something that's already existing. And it may be the case that it's a minority that's more homophilic, that has a degree advantage. And in that case, that effect will be amplified. And we can compute, a model allows us to compute like when exactly would a minority group be advantaged and to get us in closed form. But yeah, I'm not going to show here for time purposes, but I'm happy to talk more about any of these in general. So that's where this kind of models is really helping us to think about where does inequality come from, what kind of techniques can we use to find out where the connections may help a group, they may not help a particular group, and how can we formalize where inequality appears between different groups and in the degree distribution and the effects that it has on the information that people get, the recommendations they get, and so on. So this is about, I wanted to take a step back and think about like what kind of metrics are helpful here. In our case for the information diffusion project, we looked at this pipeline in which you have initial data that has some inequality. We're trying to intervene with some fairness or diversity interventions, and it was really helpful to think about statistical parity in the case of early adopters. And the model was allowing us to do so in a way that was helpful to be more efficient and fair at the same time. And it's the metrics that relate to evaluating the degree distribution that were really helpful in understanding this. But in general, that's not something that always fits in. So it really matters on what the goal, what the outcome is, and what kind of algorithms we're working with. We work on like thinking about other applications in terms of like grouping people for political groups or educational groups. And in that case, statistical parity was not really helpful for us, both in terms of like having a computationally feasible algorithm that would group people given constraint, like physical constraints and so on. And also you might not want to split the minority group into different groups in which they have like way less voting power. So that's where we looked at other metrics such as margin of victory that was really helpful in thinking about this together with the constraints that you may have. And those constraints can be, the location of people, the connections they have within their community, which turned the problem into a really difficult one, and so on. I wanted to end, and here I wanted to mention one group that I've been involved with that I think will speak to a lot of your interest as well, is Mechanism Design for Social Good. And this was co-founded by my colleagues, Fredit and Kira, but now it's a community that really grew. What we do in this group is that we think about, how do we use different disciplines in thinking about disadvantaged communities? So we think we have these working groups that work in interdisciplinary ways to think about where does computation help in allocating resources to different communities, or to design methods that may diagnose inequality and so on. And part of this is, of course, thinking about like these group connections, the way people relate to each other, the way they might relate to the people around them, the connections they form, the way they relate to an algorithm, and so on. So if that's something that you're interested in, I'd love to talk to you more about it. Recently, we also created a venue for a lot of the work that is in the scope to be published. So that's where there's a lot of our working groups on different topics. But that's where this conference came about in publishing this kind of work that may also be relevant to you. And this year it's at the second iteration and the call for papers is open. So I'd love to see some of the work that you do here as well, if you're interested. So I'm going to stop here, but thank you so much. And please feel free to contact me with any questions or any of about anything that I've talked about. And I'd love to hear your questions and thoughts.
Thank you so much. Let's go ahead and thank our speaker today. I'm going to go ahead and stop the recording there as well.